Hello everyone. In this paper, we present a quantitative machine learning approach to master students' admission for professional institutions. The motivation for this research is the fast-growing enrollment in U.S. graduate programs. According to the report from Council of Graduate Schools, between fall 2008 and fall 2018, first-time graduate enrollment in mathematics and computer sciences has increased by 11%. As a result, the admission process is becoming increasingly tedious and challenging. We want to build a model to predict student success based only on quantitative measures. By doing so, we hope to help decrease the workload of the admissions committee and remove the potential subjectivity of the committee reading the recommendation letters and statement of purpose. We build our model using information from empirically admitted students. Specifically, we use their performance measures in the graduate program as the predictive targets. The quantitative features extracted from their graduate applications, such as standardized test scores and undergraduate GPAs, will be the dependent variables. We collaborated with admission officers from Northeastern University and obtained a data set of their Masters in Computer Science program. We use a student's overall GPA in the MSCS program as his or her performance measure. Our model aims to identify the top 20% and bottom 20% performing students respectively. Table 2 presents the statistics of our data set. The total column presents the total number of admitted students for each year. The auxiliary data column presents, for each year, the number of students who applied but did not enroll. We can indeed observe the fast growth in the total number of applicants. Table 1 presents the features we collected from students' applications for our study. Feature 1 contains the students' undergraduate GPAs adjusted according to each individual university's grading scale. For example, a 3.5 out of 5 and a 7 out of 10 would result in the same value. Feature 10 contains self-reported values representing the maximum number of lines of programming written by the student prior to joining the MS program. Feature 12 contains the rankings of the undergraduate institutions where the students obtained their bachelor's degrees. We classified the rankings into 4 categories, with one being the most prestigious. The classification was performed manually according to the best global universities list published by U.S. News & World Report. The rest of the features are standardized test scores. Both the GRE and TOEFL had 2 versions of tests during 2009 to 2012 which used different scoring scales. Both of these tests are converted to their new versions of scoring scales using conversion tables provided by the ETS. 2 challenges arise when learning with this data. First, the data involves the admission committee's possibly subjective evaluation. Specifically, some members of the committee may be biased in weighing a particular set of standards, for example, GRE scores, while others may be in favor of different measures. This issue is particularly acute when the admission committee or policy changes from year to year. As a result, it can be difficult to form an accurate predictor directly from the entire data set. Since we know the instances in each bias group, we resort to the idea of SVM+ to address this challenge. SVM+ was proposed by Vapnik in 2009, under the LUPI paradigm, which stands for Learning Using Privileged Information. The idea of SVM+ is as follows. Suppose we have the privileged information that the training are the union of T groups. In addition to a shared common hyperplane, SVM+ will establish a unique correcting function for each group. Thus, the decision function for group R will be the common hyperplane, that is Wx plus b, plus the correction function, that is Wrx plus dr. Here R ranges from 1 to t. Next, the objective function and constraints for the SVM will be adjusted to reflect this correcting function for each group. Wi's and di's are additional parameters that will be learned in the training process. This diagram illustrates the SVM Plus model with two data groups. It maps data from two groups simultaneously into decision space and two correcting spaces. A common decision function is found in the decision space. In addition, each group has its unique correction function. Slack variables are represented by correcting functions defined in the correcting space. Another challenge is the limitation of the training data. We have a total of 454 labeled training samples, all admitted students, from 2009 to 2012. On the other hand, we have over 2,000 applications that are not admitted or admitted but not enrolled, which can serve as an unlabeled auxiliary data set. Our conjecture is that building a semi-supervised model leveraging the large set of unlabeled data may lead to superior performance compared to using the labeled data alone. To address this issue, we resort to the idea of S3VM proposed by Bennett in 1998. This diagram illustrates the shift of decision boundaries with and without unlabeled data. The colored dots are labeled instances, where the blue ones are from Class 1 and the green ones are from Class 2. The dashed lines form the decision boundary without unlabeled data. Once we incorporate the unlabeled data, the decision boundary shifts to the solid red lines, which in this case is more accurate. S3VM is a semi-supervised variant of SVM that learns using both labeled and unlabeled data. Formally, the SVM objective is modified to assign the best class labels to the unlabeled instances. Here Xij represents the slack if an unlabeled instance is assigned to class 1, and Zj is the slack if the instance is assigned to class -1. The overall objective selects the minimum of the two. To address both the human subjectivity and the lack of labeled data in our task, we put SVM Plus and S3VM together and introduce a new variant of SVM. We name it S3VM Plus. Our model learns with both labeled and unlabeled data like S3VM. In addition, we establish a correcting function for each bias group and incorporate them in the objective function and constraints similar to SVM+. We applied our model to the new data set and we present our experimental results compared with three baseline models, SVM, S3VM, and SVM+. Our model has the best overall performance among all models. S3VM and SVM Plus both did better than the standard SVM. From the training accuracy, we can confirm that our model has a better overall fit of the data as compared to other models. Because we utilized a linear SVM and its variants, we found it interesting to investigate the ranking and magnitude of each individual feature in the weight vectors produced by each model. Figure 1 presents the weights distribution over 12 features across 4 models. We conclude that the most important features are feature number 1, undergraduate GPA, feature number 2, GRE verbal, feature number 3, GRE quantitative, feature number 4 GRE analytical writing, and feature number 11, bachelor's degree in EECS or not. A closer examination reveals that SVM relies mostly on 3 features, they are 1, 4, and 11. S3VM has significantly large weights on 2 additional features, they are number 6, TOEFL reading and number 7, TOEFL listening, on top of the 5 features listed above. SVM Plus and S3VM Plus made use of one additional feature, which is number 9, TOEFL writing. In summary, our model, S3VM Plus, is a quantitative machine learning approach to predict candidates' potential academic performance. It is a new variant of SVM that addresses human subjectivity and lack of labeled data simultaneously. Although the performance of our approach is not perfect, our experimental results demonstrate an effective predictive model that could serve as a focus of attention tool for an admission committee. Although we based our work on a 2-year master's program, our model is easily extensible to similar tasks such as college or school admissions. Our model can also be applied to other real-world situations in which data may have clearly defined biased subgroups in a large amount of unlabeled data. Thank you. I am ready to answer any questions you may have.